Well, hello everyone. This is Calculus Fall 2020. My name is Scott Grizzard. This is Quiz Review 11A. So this one was on the L'Hopital's rule stuff. Let's pull it up. As usual, there is chat and as usual, there's chat in Blackboard Collaborate Ultra and chat in Twitch, polls in Blackboard Collaborate Ultra. Okay, so this first one here, remember this notation here. I hate this notation, but, you know, I'm not writing the test, so I have no control over the notation. So I'm using a bunch of notations to make sure that everyone gets it. Remember that this right here does not mean 1 over tan. It means arctan. So what I'm going to do is I'm going to see where this goes. To figure out where that goes, I'm going to sit here and I'm going to say, okay, I'm going to say theta, because it's an angle, equals arctan of x. And then what I'm going to do is say, okay, that means tangent of theta equals x. So I've got tangent of theta equals 0 plus, which means sine of theta over cosine of theta equals 0 plus. Now, the thing I want is 0. So I don't care what's on the bottom. The thing I care about is what's on top. Okay? So what I want here is to make sure that where I'm going is 0. Right? So here, as I come down here from the right, I want to go right, that means that sine here, right, cosine of 0 is going to be 1. I don't actually care. I care about where the 0 is. So the one I want is where the sine is 0. And sine is 0 over there at 0. So how do we feel about that? Kind of finding arctan of 0, figuring that out. Of course, you can also memorize it. That's fine too. But how do we feel about this kind of reasoning thing on that one? And if you want to memorize these other ones, there are a couple of other ones. Arctan of 0 equals 0. Arctan of infinity is pi over 2 from the left. Arctan of negative infinity is negative pi over 2 from the right. Arctan of 1 is pi over 4. Arctan of negative 1 is pi over 4. Negative pi over 4. So if you just want to kind of memorize some common arctans, that's what they are. Or you can sit there and you can reason it out. Okay. So now that I've got 0 over 0, I can apply L'Hopital's rule. I take the derivative of the top and the derivative of the bottom. And the derivative of the top is 1 over 1 plus x squared. The derivative of the bottom is 1. So I wind up with the limit as x goes to 0 plus of 1 over 1 plus x squared. So how do we feel about that, the application of L'Hopital's rule? Okay. Well, then when I put that in, I get 1 over 1. I throw in that 0. I get 0 squared. 1 over 1, and that just equals 1. All right, so that's how the problem just kind of finishes. Okay, the next one can be done 2 ways. Are there any questions, by the way? No one's been asking questions, and I want to make sure. Okay, there are kind of 2 ways to do this. The first is to throw in 0. I get 0 over 0. These are both actually 0 plus, but who cares? I do L'Hopital's rule, and I take the derivative of the top, and I get the cosine of u, where u equals x squared. Let me just do a little u equals x squared. So I do the derivative of the outside with respect to the inside. I get cosine. And then I do the derivative of x squared over, and then the derivative of the bottom is 2x. So I wind up with cosine of x squared as x goes to 0 times 2x over 2x. Now, yes, because x goes to 0. Now, I could do L'Hopital's rule again, right? Because this is going to give me 0 over 0. But why? The x squareds cancel. That's nice. I wind up with cosine of x squared. That's happy. Cosine of x squared is, as x goes to 0, is simply 1, and I'm done. All right. So 1 to 5, how do we feel about that second one? I could do L'Hopital's rule again, but why? All right. The alternative, this is so close to my special limit. I could just do alternative. Let u equals u squared. Then u goes to 0 as x goes to 0, right? X squared equals u, right? So this is x squared goes to 0 as x goes to 0. So I take this and I get limit as x goes to 0 sine x squared over x squared equals the limit as u goes to 0 sine u over u. And then I just use the special limit and I get 1. Okay. All right. So you could do it with this. Okay. So 1 to 5, how do we feel about the fact that I could have done it in another way? Oops. So the other way. I don't know if you see, there's a great Neil Simon, it's not his greatest play, but it's a good one. A Neil Simon play called Fools. And the running gag is that people keep trying to open the door the wrong way. So there's this one character that always says, the other way. Yeah, as I said, it's not the greatest play in the world, but it's it's not his best play, but it's a pretty good one. Okay. Okay, so I have a chef friend of mine, right? You can use L'Hopital's rule, but I have a chef friend of mine that says that the difference between knowledge and wisdom is knowledge is knowing that a tomato is a fruit, and wisdom is not throwing it in the fruit salad. So sometimes it's not wise, even though you know L'Hopital's rule, sometimes it's wise to not use it, to do something else, even when you can. And that's the idea. Okay. Part C here, the point is you can't use L'Hopital's rule. It's 1 over 0, and that isn't 0 over 0 or infinity over infinity. So I get 1 over 0, that's 1 over 0 plus, that's infinity. Now, I get that 0 plus, you can either reason it out using the drawing, right? This is if n is odd, 1 over x to the n looks like this. But if n is even, you get this character here. Or you could reason it out separately. Either way works. Okay. So 1 to 5 there. How do we feel about C? The big point is don't use L'Hopital's rule. No, the stuff in pink is not required. But you could do it that way. I mean, you could, if you wanted to reason it out more, you could do it that way. Okay. All right. Okay. The big thing with this one is that you're looking at the graph of the derivative. Excuse me, I'm eating my Tums. I'm old now. I have to have Tums every once in a while. Okay. So the idea here is that what I'm looking at is the graph of the derivative. Okay, I'm not looking at the graph itself. I'm not looking at f. I'm looking at f prime. Okay, so what I'm going to do is I have my handy dandy little cheat sheet that we've been doing for the last 3 weeks. If f prime is positive, that means f is increasing. And if f prime is negative, that means f is decreasing. Likewise, if f is increasing, then if f prime is increasing, that means f is concave up. And if f prime is decreasing, that means f is concave down. Okay, so 1 to 5, how do we feel about those big ideas? Okay. Okay, so what are the critical numbers for f? Not f prime. For f is where f prime of x equals 0 or f prime of x does not exist. So that would be, this is f prime. F prime exists everywhere on this thing, but right there and right there are my critical numbers. Okay. All right, so how do we feel about that? So this is critical numbers. Are there any questions? It always makes me suspicious when no one asks questions. Where is f increasing? Well, that's where f prime is above the axis. So that's negative 2, 0. From negative 2 to 0, and from 3 to 4. And you can see I made little notes here, right? Based on this table right here, I made some notes. Wherever f prime was greater than 0, f would be increasing. Here I'm negative, that means f is decreasing. And here I'm positive again, that means f is increasing. Here I'm decreasing, so that means f is concave down. Here I'm increasing, that means f is concave up. Okay, so how do we feel about number B there, 1 to 5? So okay. Okay. Where does f have a local min? Well, local mins happen when I go down and then I go up. So that means that f prime went negative and then positive. So I'm looking over here. Here I went up and then down. Here I have a max. And here I went down and then up. Here's where I've got a min. Okay, so that's at x equals 3. And I can actually do this right here. This is enough justification for that. I don't need to say where f prime goes from negative to positive. I can just write that. Okay, so 1 to 5, how do we feel about the min-max thing there? Okay. And remember, I'm looking at f prime in the graph. The graph is of f prime, not of f. I'm asking questions about f, but I'm looking at f prime. Okay. Now, for concave up, I want where f prime is increasing, F prime is increasing from 2 to 4. So that's where I'm concave up. So that's where F is concave up. So how do we feel about that? 1 to 5. Okay. All right. Now, for what x values does f have an inflection point? Now, there are lots of ways to think about this. There are lots of good ways to think about inflection points. The definition is where the concavity changes. But the easiest way to think of an inflection point, the easiest way, is that is where f prime has either a minimum or a maximum. Okay? That's the easiest way to think about it. F prime has a minimum or a maximum. All right? If I've got a nice differentiable function like I do here. Now, there's, sometimes you can have a jump that has a concavity thing, but, for this purposes, if you think about where f prime has a min or max, it will keep you from messing up a lot of places. If you don't try to keep there, well, f double prime equals 0, and then on the left it's concave. You can solve a lot of these just by thinking about f prime changing from increasing to decreasing or decreasing to increasing. That way, the thought process of thinking about concavity is the same as the thought process thinking about increasing, decreasing. You just take another derivative. Okay, so for increasing, decreasing, you look at the derivative of f. For concave up and concave down, you look at the derivative of f prime, which is, of course, f double prime. So if you just think about those things, it actually helps. Okay, it's easiest to think of them as local mins and local maxes on the first derivative, of the first derivative. So how do we feel about E there, 1 to 5? And are there any questions? Okay. Right, so this is not a closed set. There's a good question that we might have, f prime might have a min or max. Yes, except that if it's one of the endpoints, you don't care because it's not really an inflection point, right? And it's not the absolute mins and absolute maxes you're looking for. It's the relative, it's the local mins and maxes, right? It's not the global, it's the local mins and maxes. And of course, global ones are local, but you don't actually care about what's going on at the endpoints. You only care about what's going on in the interior when you're talking about inflection points. By the way, that C1 function means a function that is continuously differentiable. If someone's asking what that means, that's what C1 means. It means that it's a function that has a derivative and its derivative is continuous. As a response to what the person was asking there in chat. Are there any other questions? Okay. All right. So that's it for the stream. I'm going to talk to you all about the problem set real fast in Blackboard.